Okay, welcome everyone. So today we are very pleased to have this opportunity to introduce our work for the cloud storage acceleration layer, which we call the CSAL. It's a joint work between Alibaba Cloud and the Intel Corporation. So the CSAL enables the unprecedented performance and capacity values with Optane and QLC flash disks. And also helps Alibaba Cloud to provide a new instance with very great efficient data analysis computing instance. And my name is Qinghua from Alibaba Cloud, and this is the Kapil from Intel Corporation. Would you like to? Yeah. Okay. So many team members from both Alibaba Cloud and Intel Corporation have worked on this project. I would like to take this opportunity to thank everyone who contributed to this work. And this is our agenda today. So first, I will introduce a little bit about the background and the motivation of our work, and begin with a little bit of background of Alibaba Cloud local storage product. And then I will discuss the trend and the challenges with big data computing instance. And then we will talk about how we adjust the NAND density and the scale challenges. And finally, I will introduce the new D-series big data instance from Alibaba Cloud. And in the second part, Kapil will introduce the CSAL architecture overview and also provide some performance evaluations. Now let's start with some background and motivation. So let's first take a look at the Alibaba Cloud local storage products. Different from the Alibaba Cloud disks, in the Alibaba Cloud local storage products, the physical storage devices are directly attached to the physical servers where the elastic computing instance is running on. So there are two families of instance that with local disks, come with local storage disks. The first one is I-series. This instance equipped with high performance and local NVMe SSDs that delivers high I/O throughput and low latency local disks. They are designed for the OLTP or OLAP database workloads. For example, the MySQL and Aerospike and also Ant Financial Ocean-based are the typical workloads that's running on this type of I-series instances. The second ECS family with local disks is the D-series. Compared to the I-series, they have high capacity and a relatively low throughput local disks. But they are designed for big data and offline analysis, like HDFS, HBase, ClickHouse, or Elastic MapReduce, or Spark and Hadoop. So below diagram shows the difference between the I-series and the D-series instance with local disks in terms of the performance and the computing relative to the storage capacity. So as you can see, compared to the D-series, the I-series have much higher performance and virtual CPU and the storage capacity ratio. So in this talk, we will introduce the D3C instance and the technology used in this instance that we have been working with Intel partners to resolve the challenges that we have in cloud data centers. So now let's discuss the trend and the challenges that big data analysis workloads brings for our computing instance. So as we know, the CPU is moving into the next generation technology. For example, from the Cascade Lake to Ice Lake, where the number of CPU number of CPU cores is increasing, and each CPU is more efficient than their previous generations. And also with the PCI Express evolving from generation 3 to generation 4 or even more. So all these result in more accelerated computing performance growth. So with this accelerated computing growth, so our design goal is to fully utilize the power of compute to make the big data analysis workload run faster and analyze more data in less time. So to do that, maybe we should add more disk capacities and also with improved disk throughput. Because for typical big data workloads like elastic MapReduce, there are lots of temporary data that need to be read into the local disks. So they need more kind of storage capacity and throughput to scale up and utilize the full computer capacity. So on the other hand, so we cannot just upgrade the previous generation of instance with more hard drives. Because previous instance, we enable the local disk with hard drives. Because the rack space limitation, we cannot just add the more disks. But if we use the similar number of hard drive disks, the throughput per terabyte will decrease actually. For example, if in previous case, we are using 2 terabyte hard drive disks for each instance. There's total 24 such disks in one instance. But if we use 8 terabytes disks, hard drive disks, then the throughput per terabyte actually will be decreased from 125 megabytes per second to 31 megabytes per second. So that means you didn't get more performance when you add more capacity. So this is not kind of what we want. But fortunately, with the high capacity and the low cost QLC NAND SSD disks, that gives us an alternate solution to this problem. So we can easily use 8 16 terabyte QLC SSD disks to provide 128 terabyte storage to one physical server. And in this case, then we can still keep the previous 125 megabytes per second per terabytes. So that's the way we are going to do. But however, as we move into the QLC SSD from HDD disks, things are not as easy as we originally thought, because both the QLC performance and endurance becomes the new challenges. So here we analyze the performance problems of QLC SSDs. So on the left, here are 2 configurations we use to compare the performance. So on the top is the configuration using 2 terabyte hard drive for each virtual disk in the guest OS. And then the second is using 2 terabyte partition from a 16 terabyte QLC disk for each virtual disk in the guest OS. And we run 8 same kind of workloads of FIO with Q depths of 128 in guest OS. We're trying to measure the performance difference between hard drive and QLC. So as you can see from these 2 diagrams, we can see that the sequential rise actually are even lower than HDD hard drive for small block sizes. And for the random rise, also not optimal, especially for the small block sizes. So that means directly applying QLC SSDs into the local storage seems hard, as it's not as expected as we hope. So what might cause these two problems? So we analyzed and we found that the basic cause is the extra write amplification. So there's 2 problems that cause these write amplifications. The first one is non-optimal writes. For example, the small writes or misaligned writes caused by the internal interaction unit, because the internal interaction unit is the internal logic to physical translation entry granularity. So the large entry, the large IU actually helps to reduce the DRAM that needed to translate the table. But increase this IU may introduce random amplification for non-optimal writes. For example, the Intel P5316 uses 64 IU. If user writes a 4K size, take this example, then this controller will need to fetch the whole 64 data from one interaction unit from the media and to the cache, to the DRAM, and then make the in-place update of 4K, and then write back the 64 kilobytes data into the media again. So this involves 16 times write amplification. So for the misaligned writes, basically is similar. For example, although the user can write 64 kilobytes data into the disk, but if the start of this write offset is different than the interaction unit, this will cause the misaligned overhead. The controller has to read two 64 kilobytes data from the media and then apply the 64 changes to these two kind of units, and then write 128 kilobytes back to the media. So although the write size is same as interaction unit, but the write amplification is true in this case. So the second cause is the multi-tenant problem that's caused by the internal flash translation layer. Is also a problem for this case, because in our case, because of the QLC SSD drive is large, it can be shared by multiple virtual machines or multiple virtual disks. So they got kind of partitioned into different smaller disks. So in this case, the device manager FLP will mix the requests from multiple virtual disks into one stream. And this introduces the extra write amplification, because the data in different tenant or different virtual disks usually have different life cycle. So mixing these IOs into the same erase block will cause extra write amplification when internal garbage collection process starts. For example, if the virtual machine from two deletes some data in one erase block, then the garbage collection have to rewrite the data from other virtual devices into the other places to make kind of garbage collection. So how can we address this problem? So we worked with Intel to resolve these performance and endurance challenges. So we worked on a project called CSAL. The CSAL is the cloud storage acceleration layer. So with the CSAL, it provides the flexible scaling of NAND performance and the capacity to the user and the workload needs. And also, CSAL provides an Optane ultra-fast cache device, and also embedded write shaping technology to improve the system performance while reducing the cost, scaling QLC value. This kind of zero native storage delivers no compromises I/O performance. And also with the multi-tenant QoS software, this enables 8 times drive density, resulting in 3 times rack savings. So this is one example of a configuration. So basically, in CSAL, we can use 800 gigabyte Optane disks, work with 116 terabyte QLC to form a virtual disk, provide to the server. And then one server can have 8 sets of these configuration, which totally provide 128 8 terabyte storage. So the left diagram shows the evaluation of 10 typical workloads on a low block device with CSAL and the Optane cache. So as you can see, for the 4K random writes, the CSAL shows the 35 times performance of that of QLC itself. And then for 64K ZipF 1.2 random writes, that is high locality workloads, the CSAL shows 8 times performance of that of QLC. So that's great, right? So based on this technology, we released a new D-series big data instance this year. So compared to the last generation of the D2C, which is enabled by the hard drive, so user can basically pay almost the same price per gigabyte to enjoy the Optane and the QLC performance powered by the CSAL technology. So also, as the computer and the storage density increase, and the one physical server that could provide 2 largest standard instances, as shown here, the one physical server with 64-core S-Lake CPU and the 128 terabyte storage can provide 2 instances, each instance with 56 virtual CPU and 64 terabyte storage. And in previous generation, there's one physical server with 48 cores with Cascade Lake CPU, and the 48 terabyte storage can only provide one largest instance, which you have 96 virtual CPU and 48 terabyte storage. So although the instance looks as a little bit different, but we evaluate them with 2 typical TPC workloads. That is kind of data analysis workloads. So for the TPC-XHS, which is storage intensive workloads, we can see from the new D3C instance, the largest instance, can achieve 103% more improvements in terms of the total time and also the H-sort process. And for the TPC-DS, which is computer-intensive workloads, although we have less virtual CPU, but because we have more bandwidth, right, and we can have almost same performance as the older instance, which have more CPU. So next, Kapil will introduce the technical architecture of the CSAL and give the performance evaluation. Yes.
So my name is Kapil Karkara. I am from Intel Corporation. I'm a principal engineer, and I actually worked on this technology called Cloud Storage Acceleration Layer. I want to extend my thanks to Team Alibaba, PRC team at Alibaba, and I actually thank to Tsinghua, who actually is covering for some of our PRC Alibaba colleagues who couldn't make it today. Yanbo and Lee especially, who worked with us and have worked with us since April of 2021 to create this technology. Before I dive into the architecture, this is it because I'm moving or I put it in my pocket, no? No. So where should I place this? Okay. Can you still hear me? Yes, all right, thank you. So just to, at a high level, I wanted to talk about, before I talk about the architecture, CSAL is actually a BDEV inside Storage Performance Development Kit, SPDK. And basically, a single instance of CSAL will bind to some compute resources, for example, certain DRAM and certain virtual CPUs. And then it'll basically also bind to 2 tiers of storage. And once you have created this scale-out unit, then it will scale linearly as you go create more CSAL instances to get the performance up. So let's dive into the CSAL architecture here. So this architecturally should seem very familiar to you for SSD vendors especially. It's like what SSD vendors do inside their SSDs. It's a flash translation layer. And the main difference is that we are up-leveling this FTL to the server level or some kind of platform. You can think of this as a 1 petabyte SSD, and this flash translation layer will be able to create 1,000 1 terabyte high-performance SSDs out of it. And those 1,000 1 terabyte SSDs can be served up to multiple tenants, multiple cloud tenants. That's the key idea here. So there are 6 architectural components that I'm going to lay out one by one. The very first component is flash translation layer itself. So on the top end of this flash translation layer, we basically present a block interface. It's a 4K sector size block interface that applications are very familiar with using, so no change to the applications. We then land all those writes to a persistent write buffer tier or cache tier. And this is where, in the current deployment, we're using Optane SSDs. Going forward, we want to use SCM SSDs. And once you have landed the random writes to this cache tier, from there you can aggregate, merge small writes into large ones, and write in aligned, correctly sized, that very NAND-friendly manner down to the NAND tier. So we've been using Solidigm's P5316 drives. These are 64K indirection unit drives. And if you, like Tsinghua kind of mentioned, if you do anything less than 64K, there will be an internal fragmentation or read, modify, write penalty. And we completely avoid that by actually merging and writing. This cache is actually a log structured cache because we have the full L2P index. We can do basically a log structured cache that has advantages over associative caches. Now, as any FTL has to do, we do garbage collection. We have several different algorithms to do this. We also implement a power fail crash recovery. And then most importantly, there are some advanced DevOps cloud-like capabilities. For example, a live software upgrade, or if SPDK process crashes, we can recover within half a second. And we can stand up another instance in half a second and get running, so the vhost clients will not be impacted or will not see a difference. So that's the first component. Second component is the logical to physical mapping table. So any FTL has to carry this logical to physical mapping. It's mapping the user LBAs to physical LBAs on the media. And if we have to do a 1 petabyte flash management, we will need we do 4 bytes per sector, so we will need about 1 terabyte of DRAM if we were to keep entire L2P index in DRAM. So that's going to be very costly, so we did tiered logical to physical mapping table where we page in and page out to a partition on Optane SSD or SCM SSD, all this paging page out, and we keep small percentage hot portions of logical to physical mapping table in DRAM. So that's the second component, logical to physical mapping table. The third component is the persistent write buffer / cache tier. So this enables the early write acknowledgement. You can basically land all writes to the fast SSD and complete the write to the user application. This provides time to durability. It shortens the time to durability. And most importantly, it is a cache. That means it will absorb a lot of temporary writes. So what we observed in big data workloads, I think Tsinghua also mentioned, that these You can think of big data workloads as doing a compute graph where there are multiple compute tasks where one stage of the pipeline will create a lot of intermediate data, dump it to the storage, and then following stage will read it out back, and so on. So what happens is the goal here is to capture all that intermediate data in Optane or SCM tier. And it has two advantages. That data will never actually need to be flushed to the QLC tier. And second, it will basically be read out of a faster media. So you get performance and endurance benefits, as in lifetime of the QLC drives will significantly increase. Okay, and then the fourth component is this storage analytics layer. This is where we basically have some advanced algorithms to manage quality of service, provide bandwidth consistency, and such. And we are adding tenant isolation and some of the other interesting I/O scheduling type of things. That's basically going to be part of eventually our upstream implementation. Right now, things in orange are like, that's where we are targeting, marching toward, but in the current implementation, a couple of those things are not present. Then the final piece of it is where you're getting all the cost advantage is going to this high density NAND. That's what we're trying to enable here. And QLC drives that we are using today are pre-ZNS drives. We are using Solidigm's P5316, they're 64 IU. So they do get some kind of DRAM reduction benefit on SSD DRAM reduction because their L2P map is at not 4K sector granularity, but 64K sector granularity. And we can also reduce the over-provisioning on these drives because our FTL takes all the write amplification. We sequentially write to the SSD. SSD level WAF is 1, basically. The idea going forward is to use ZNS SSDs. And ZNS SSDs really unlock the full potential of this SPDK FTL. We understand that from the ZNS SSDs that we have been using, and I'll show you some of the early results. Basically, we will have the DRAM reductions are higher because ZNS doesn't need to keep the full logical to physical mapping table on SSD. The OP is going to be 0. PLI protection, because we have the persistent write buffer here, PLI circuitry, PLI logic can be simplified on the SSD level. We basically also, what I'm hearing in the ZNS implementation is that implementing XOR, die-level XOR on those SSDs is really difficult. So there will be no XOR in the PLC, HLC, QLC type of ZNS drives. So basically, we will have a highly cost optimized with ZNS, highly cost optimized flash tier. And so because the XOR is eliminated from the drives, we pick it up. We are implementing RAID 5F, we are calling it RAID 5, full stripe RAID 5, because you see how we have the data in the persistent write buffer. We don't have to implement this read modify write RAID 5. We can always ensure full stripe writes. So if you know that for a read modify write sequence of RAID 5, you have to do parity writes multiple times. Every time you do a small read modify write sequence, a parity becomes a hot stream kind of thing. You have to so write amplification at the RAID layer is because you keep writing parity over and over. That is eliminated in this particular implementation of RAID 5. It's 2 to 3x more performant than the traditional RAID because we don't have to do reads and additional writes to parities. We also do this for one more reason. One reason is, of course, we are dropping XOR from SSDs to bring up the Uber and reliability. We implement the XOR. But then the second reason is, as you think of these SSDs that are getting 100 terabyte, 64 terabyte, large capacities, when one of these SSDs fails, then you have to rebuild this. It'll tax the network, east-west network bandwidth quite a bit. So having a local RAID starts to make sense from that point of view too. There are other kind of advantages of this because we have a full stripe RAID. We never have the RAID write hole problem, so to speak. For RAID write hole, you have to do additional journaling writes and things like that. We don't have to do those because we are doing full stripe RAID 5. So in summary, really what we have done here is we have really this translation layer, this flash translation layer in SPDK will enable this high density NAND going forward. Because we already support like ZNS interface, we can sequentialize the ZNS or the flash tier can be much more cost optimized, and we implement that FTL and RAID and caching to kind of provide that capability. You can think of this as a NVMe over fabrics target. Targets can use this flash translation layer, and that's basically the SSD of the rack. NVMe over fabrics targets will disaggregate. That becomes the SSD of the rack, and this is that flash translation there. We hope that powers those NVMe over fabrics targets. So next I wanted to go to the evaluation, but maybe I can pause here for any quick questions you might have, and then I'll drill down into some of the results that Xinghua already showed, but we can drill down into that basically. Okay. So let me show you the results here. So these are 10 tests that actually Alibaba gave us. Some of these tests are corner cases, and these are simple FIO scripts. It's very familiar kind of FIO scripts. Some of these tests are corner cases, but some of these tests are what Alibaba's customers use to evaluate their local disk service. And let's look at the test number 4 first. And this is basically a Zipfian distribution workload. Theta is 1.2, which means basically more than 90% of the accesses are to, let's say, 10%, less than 10% of the LBAs. Very popular LBAs are being hit over and over, very cache-friendly workload. And this is the kind of workload that mimics what I was giving you the example before, where you have a lot of temporary data being created, read out and deleted, created, read out and deleted. So a lot of these, this is basically mimicking that kind of workload. And you can see we get, so just to quickly orient, back up and orient this table, we have, like Xinghua mentioned, on the first column we have 8x HDD. So in the D2C service, which is the local disk service, second generation from Alibaba, they have been using 8 hard drives, 8 2 terabyte hard drives, and we are replacing that with 1 16 terabyte QLC drive. So that's basically the same 16 terabyte service, same 16 terabyte capacity. And that's the middle column. If you just were to use a flat TLC and compare that with 8 HDDs, that's the middle column. And then you can see that the third column is where our CSAL, caching, and FTL is working. So in this case, because we are capturing a lot of the temporary writes or popular LBA writes are actually just captured in Optane SSD or cached here, and less and less data is going to the QLC. We get a lot of endurance or lifetime improvement of the QLC useful life, as well as about 8x performance advantage over just flat QLC. And by the way, if you notice, this workload is not a 4K random, but rather a 64K random aligned to the 64K IU of the drive. So we're not really incurring any internal fragmentation or read modify write penalty of a 64K IU QLC in this case. And we are about 8x better there. Okay, so if this is good, so then we can go to, this benefit is really from caching, capturing that intermediate writes into the Optane SSD cache. These results are from Optane SSD. Okay, so second, I want to focus on number 6. This is a very popular one of the four corners workload, 4K random writes. And you can see 35x improvement over QLC. HDDs, you expect very low performance here, 1.2 megabytes per tenant. And when you go to QLC by itself, it's actually 3 megabytes per tenant. And this is that missized, misaligned write problem. With 64K, when you do 4K, you get basically straight up 16x write amp because of read modify write. And then some of the multi-tenancy is causing further trouble, further pain for the QLC. And you can see we get about whopping 35x improvement over this workload with our CSAL implementation. Okay. Next, let's see. Okay, what happens to mixed workloads where we have both reads and writes? In this case, the QLC workload is invariant, fixed 64K sequential workload. So CSAL basically generates a very invariant sequential workload to the QLC tier. It's sequential, it's 64K IU size writes, and it's aligned. So very NAND-friendly, WAF on the SSD will be 1. And what it does is it actually keeps the read-write collisions, it mitigates the read-write collisions. Most especially, the internal garbage collection in the SSD is completely mitigated because the write amp, we're providing a WAF 1 workload to the SSD. We're writing sequentially to the SSD like a log, and it's a self-invalidating workload. So there is no internal garbage collection running on the QLC drives, and therefore we get much better performance, much better read performance in the presence of writes. You can see about 4x improvement there. And then lastly, I want to talk about this sequential workload. This is an interesting one. This is the case where actually QLC drive by itself was underperforming the SSDs, HDDs. A single HDD can deliver about 250 megabytes per second. So 8 of them to 8 tenants, each HDD bound to a single tenant was giving 250 megabytes per second to each tenant. But when we consolidated that over a single QLC, you see this mixing effect, especially when you're doing 4 kilobyte sequential. There is this, the transfer buffer on the SSD or other nuances are not able to keep up. And ultimately, QLC sees this multi-tenant workload, even though it is sequential within itself, it gets mixed and it's perceived by, it gets presented to the QLC as random. And that's what the performance is, like 5 megabytes per second per tenant. And we get 70x improvement in this case. And this is where, I'm calling it coarse-grained multi-tenancy. So like Xinghua actually presented that if you look at if you don't look at this micro benchmark, if you look at his macro benchmark, which is the big data workloads, he ran TPCX-HS and TPC-DS. We got the density benefit because 8 HDDs were consolidated into a single QLC. That's where the density benefit is coming from. And then we kind of enabled this multi-tenancy because by itself QLC couldn't sustain these multiple tenants. But with our flash translation layer, doing this any workload to kind of invariant workload translation, we are able to achieve this coarse-grained multi-tenancy. Why I call it coarse-grained is because there is still a single pen when RFTL drains the data to the QLC tier, there's still one pen. It's not a ZNS like we can isolate to different zones, different lifetime streams. That's not available today in these SSDs. But with ZNS, we could do much finer grained tenant isolation. And that's where basically I want to thank our Western Digital friends. Matthias is not here today, but we got a ZNS ZN-S540 4 terabyte drive from them. Now these are true multiple tenants doing not just sequential, but basically different workloads. We mixed basically a sequential with a random with a with the popularity LBA kind of workloads. And when they all get mixed, you observe a WAF of about 3.8, and on a same drive but regular firmware. And when we do ZNS firmware on the same drive, we end up with a significant improvement on WAF. We don't have performance, but we're working on that right now. This is preliminary data, but the FTL is ZNS ready. Okay, and so we are really, I want to say, getting started with the CSAL, right? So we are upstreaming by the December, the end of the year SPDK release will have the BDEV, FTL BDEV upstreamed. And we are working on a RAID 5F and a RAID 1 for if you wanted to protect and improve the reliability of the persistent write buffer itself, cache itself. And we plan to do by the second half of next year, we should have a NVMe Fabrics reference solution as well. And that's what we are working toward. In terms of references, I have included a couple of these references for you to do some additional, if you're interested in additional study here. We have a paper and a couple of presentations. And that concludes our talk. We're happy to take questions now. It's getting late here. Any questions? So yeah, great question. So question is, how do we see, how does basically SLC drive compares to Optane in terms of performance, endurance, in the presence of this kind of workload? So great question. We have been evaluating some SLC drives. The fundamental thing, I mean, they are performing well. We are not seeing a lot of WAF. Some of these SLC drives are highly over-provisioned where we are testing. So we're seeing actually pretty close to what we were getting with 800 gigabyte Optane SSDs, older stream drives. We're getting similar performance. The real issue is there are two things I will mention. One is that, okay, our log structured cache workload is really sequential. We're just writing as a log to the so that's very SLC friendly. Our cache user data caching workload. Because it's a log structured cache, we're just laying it like a log. The paging of L2P index, paging in and paging out, that's a random workload. And the impact of that random when that gets mixed with our sequential cache workload is not that bad. Let's just say that. And we are evaluating aggressively with other SLC drives, etc. Great question. So if it's very fast and it's very expensive, it's not quite as interesting as very fast. Yeah, so the idea is that as you go to 4 bits per cell, 5 bits per cell, 6 bits per cell, and ZNS, hopefully the cost of flash will go down. And the idea is that, okay, we are using some SCM SSDs to cache. That will provide the performance and endurance part, right? That's the performance and endurance help that you're getting with caching. We do carry also the full logical to physical mapping table. So those are two cost adders. But then it depends what you're comparing it with. If you're comparing it with a flat TLC, for example. I'm comparing the performance table. I see. Yeah, it's very competitive to TLC, let's say, a flat TLC. If you were to, and going forward, it'll only get better. As you, right. No TLC there, correct. So that's where, oh, I see. So you're asking between HDDs and QLC? I see. So maybe Xinghua, you can address that a little bit.
So I assume you're talking about this diagram.
Yeah, I mean, so basically, but what he's asking is, okay, that's actually a great question. So yeah, this table. So in this table, basically, what's the difference between first, second, and third in terms of cost, right?
Yeah, basically, actually, as we mentioned in the last previous slides, so customer basically can pay the similar price per gigabyte. Very similar. So actually, before it's very similar, and right now, because we want to differentiate the instance, we charge a little bit more, but in terms of cost, it's very similar per gigabyte. Per IOPS, that's a great question. I have to go back and check.
So let me just make sure. So basically, if you compare D2C, so what Xinghua said is that D2C was HDD based, and they can sell the service at the same price to their customers. The D3C service, which is powered by the CSAL and QLC. But you get, if you go back to the big data workload results, right, you get 2x density because you can put the two of those largest instances in the node versus one. So, and then you also get double the performance. There was 103% performance gain. That's doubling the performance. So you're doubling the density, doubling the performance for the same price from customer point of view. For the big data workload, right? Big data, this was a big data workload. Yeah, so this is a big data service, really. The whole D3C, D2C is a big data service. Yes?
So one thing that sticks out a lot here is the CPU reduction from 96 to 56 vCPU when you went from cascade link to isolate. Can you talk a little bit more about what efficiency we're gaining there that led to that?
Okay, so the question is, for these two instances, the virtual CPU number is different, right? What's why we can achieve the similar kind of performance or even better performance? So the key thing is here. So for the older generation, that is D2C, actually, although we have smaller, we kind of similar storage, but because the storage throughput is much lower than what in the new instance, the CPU or the virtual CPU, although we have more cost, but it is not fully utilized. That's the motivation we mentioned before. So with the new generation, each core can have more behave more efficient, and with the larger storage throughput, the performance for these workloads can achieve much better performance.
So just to make sure, maybe can I rephrase that there are two benefits are coming from two. You're going to faster processor, and the workload was storage bound before. HDDs were basically, you would see I/O weights and things like that in the workload. So you go you also eliminate the storage bottleneck by going to QLC.
Any more questions? Okay, thank you. Thanks everyone for attending our session.